All right, thank you for your endurance. You have my respect. I know this has been a long week for you guys. All right, so let me remind you, what remains to be proved is the following thing. Let's call this 1, that the L1 norm on QR of the localized half derivative applied to AH, this thing we defined at the end of the hour last time, is controlled by the measure of QR. Notice, of course, that this is like R to the D. Notice here at this point, we no longer need to restrict to F inside of QR because the F was only used to do this Marcinkiewicz integral business. All right, once we've got A replaced by AH, we don't have to have that restriction anymore. Okay, so as before, we're going to let PR be a nice parabolic approximate identity. On Rn with a kernel that's even in the x variable. All right? I'm going to let gamma positive be a sufficiently small constant. All right, and then I make the following observation. Since in particular, H is parabolically Lipschitz, in fact, it's R-lip, but in particular, it's Lipschitz. If we look at the L infinity norm of the difference between P gamma R, P is this approximate identity, minus H, right? So P gamma R minus the identity applied to H, it's going to be less than or equal to a const times gamma R. All right. And if we choose gamma small enough, this will be strictly less than 1/2 R for gamma small enough. Some absolute constant gamma. Okay. So therefore, for R bigger than 0, we have this. We have that R plus P gamma R of H is strictly bigger than R over 2 plus H, which of course is bigger than or equal to the max of R over 2 and H. And notice the key takeaway here is that this guy is strictly bigger than H, which means that the point R plus P gamma R H of xt, comma x comma t, is in our domain omega 1. That's this domain for the half space, right? That lifted up to give us to lie inside of omega star when we lifted it. Okay? And this is for all R positive. Okay? Because the vertical component is bigger than H, and that's the definition of omega 1. All right. So now the next lemma, various square function bounds for H or really Carlson measure bounds, I should say, that for all Q and Rn, we have the following. Okay, uniformly in Q, of course. Okay, so this is a Carlson measure estimate for this measure. All right, and second, we're going to have various versions of this. dr PR of h squared, and I won't keep writing it out, but it's always this same underlying thing. This will also be less than or equal to the measure of q. Third, again, integrate over the Carlson region in the half space of, well, let me summarize it here. If we have any number of derivatives applied to PR of h, dr over r, dx, dt, again, this will be less than or equal to the measure of q, provided that either j is bigger than or equal to 1 and m is bigger than or equal to 0. These are, j and m are integers, of course. Or j plus m is at least 2. Okay? And finally, fourth, we have size bounds for these guys. One of our r, PR minus I of h L infinity plus dr PR of h and L infinity plus r to the 2j plus m minus 1 spatial gradient to the m power time derivative to the j power of PR of h and L infinity. All of these bounded by some uniform constant. Of course, well, uniform. Of course, this will depend on j and m, okay? Just as this one does, obviously, okay? And the proof, I'm just going to give you a sketch because you really know already how to prove this. Okay, the key factor is that, remember we insisted that the kernel of our approximate identity be even in the space variable, okay? All right, since the kernel of PR is even in X, that means in all of these expressions, we can always replace H by H minus L, where L is an affine, well, L is any affine function of X only. All right, and then we just use the converse direction of lemma 5. Okay, these size estimates are even easier. It's just the parabolic Lipschitz property of H lets you do that. Okay, and the fact that always you can replace H by H minus a constant because you're always dealing with something that kills constants. All right. Okay. All right, next lemma. Well, first a definition. I'm going to set a tilde of Rxt to be A of R plus P gamma R H of xt, xt. By the way, maybe I should make a historical comment. If you're wondering what's going on with this thing, where I've replaced H by some regularization of H, some smooth approximate identity averaging operator applied to H. So this is a kind of a change of variable that has been useful in PD, both elliptic and parabolic. That goes back, I guess, to maybe Dahlberg and Koenig and Stein. So this just didn't just come out of thin air. It's useful because it means that derivatives applied to this guy eventually are going to have square function bounds, and that's why we're introducing it rather than just having H itself. Okay, that's actually the content of this lemma 11. The fact that we're going to have things for which we have Carlson measure estimates, which we would not necessarily have just sticking derivatives on the H. Okay. All right. For H, we have from lemma 5, we have the betas based on H minus an affine function. We know we can control that, but putting derivatives on the H directly isn't necessarily going to give us Carlson measure estimates. So that's where this mysterious thing is coming from. Okay. All right. So A tilde is going to be this guy. All right. Let's notice that at R equals 0, A tilde of 0 xt, well, what's happening? At R equals 0, that's 0. This is an approximate identity. So as R goes to 0, this just goes to H. So this is simply A of H of xt, xt. And notice, remember, that's by definition, this is the thing we were calling AH of xt. Okay? All right. So here's lemma 12. So we had this earlier lemma 9, which basically was stating the analog of the things I'm about to write for A of Rxt, and now they're also going to hold for the A tilde of Rxt. All right. So this is basically, it's going to look familiar. It's basically lemma 9, but with A of Rxt replaced by A tilde. Okay. Which is, of course, R to the D. All right. Oh, and second, there's size estimates, too. If we look at R, dr squared, U tilde of R in L infinity norm plus R dt, A tilde L infinity norm plus R squared dr dt of A tilde. All of those are going to be bound by 1 or by some uniform constant. All right. And so the proof, again, I'll just sketch it because this is a pretty routine exercise based on what we've already stated, what we've already done. Okay. The proof is just the chain rule plus lemma 8, lemma 9, and lemma 11. Okay. And by the way, so here we're using the thing that I called 3, which is not here anymore, but which said that R plus P gamma RH of xt was in omega 1, which is a place where we know, in omega 1, we know some good things, all right? So what's going on here when I say it's just the chain rule in these lemmas? Well, think about what happens when you differentiate this guy. So when you do either x or t derivatives, well, here it's just going to be like differentiating AR of xt, A of RXT. But you also have this extra terms where derivatives hit here, and then you produce derivatives of P gamma R of H. Okay? But then you do that, and you carry out the chain rule, and you apply these derivatives, and what's going to happen is either you're going to have at least a couple of derivatives or a time derivative on A itself, or you're going to have it on this guy. Okay? And so when you have enough derivatives on the A itself, you're using the Carlson measure estimates in lemma 9. When you have enough derivatives on the H, or on the P gamma R of H, you're using lemma 11. And the other factors are going to be bounded because, well, of property 4 there, which gives you bounds on the derivatives for H, and then lemma 8 gave you bounds on the derivatives for A. Okay, so I just leave this as a routine exercise. Okay. All right. All right, so let's recall what we're proving. Remember, it remains to prove. This thing that I'd called estimate 1 a moment ago, which is the L1 estimate for the localized half-order derivative applied to AH. Okay? So, of course, then trivially by Cauchy-Schwarz or Jensen's inequality, it's enough to prove an L2 version. Which I'll call maybe 1 prime. And we're going to do this by dualizing. It's equivalent to proof. Maybe I'll call it 1 double prime. That if we look at the integral, this is in Rn, of dn R of AH times some function f, dx dt, that this is less than or equal to, I think I need to maybe resort to this guy for a second, because this is just not getting clean. We'll have to live with it. Okay, so that it's enough to prove that this is less than or equal to the square root of the measure of QR times the L2 norm of F for F in L2 of QR. So an L2 function supported in QR. All right. Okay. So we'll give this a chance to dry. All right, so we're sort of going to mimic what we did in lemma 5. We're going to extend up into the half space. This is in the proof of lemma 5. We integrate to extend up into the half space. And then we have dr of dn of a tilde of r dot. And here we're using, well, maybe I'll write this down and say what I've done. So here where we're using, okay, then plus a boundary term. So let me call this the main term plus B1 for the first boundary term. Where what am I using here? We are using that, as I noted above, a tilde of 0xt is AH of xt. Right, so when you're down at r equals 0, you're getting AH. Okay, so that's why this works. All right, so the boundary term B1 is equal to minus integral Rn of dnr of a tilde at 5r times p 5r of f dx dt. And so now let me recall that the kernel of dn of r was a time derivative of a truncated fractional integral, right? So dnr applied to AH. No, I don't want AH. A tilde of 5r is equal to dt times VR convolved with a tilde, right? Where VR, once again, is v times phi. V was the kernel of the fractional integral. Phi was this smooth cutoff function that localized it. All right. And of course, for convolutions, this is a convolution both space and time. So we can move the time derivative over here. All right. So this is the same as VR convolved with dt of A tilde at 5R. Okay? And I claim, and I'm going to leave this as an easy exercise again, that this is bounded by some uniform constant. You're just using lemma 8, parts 2 and 4. Just size estimates, right, for derivatives of A. And remember, A tilde is based on A. All right, plus the size and compact support of VR. Okay? And you just check and it just works. It's easy. It's routine. Okay? All right. All right, so the main term. Oh, wait, I need to say the punchline for the boundary term. I'm sorry. Okay. So for the boundary term, what does this tell us? This tells us that this first factor is bounded. Okay? So hence, B1 in absolute value is controlled by just the just the L1 norm of P5R of F. And notice that's supported in the cube Q6R, say, because F itself was supported in QR. This is a complexly supported kernel, which is supported in a parabolic ball of radius 5R. Okay, so this is localized. All right, so then we just use Cauchy-Schwarz. And then of course, we use that an approximate identity applied to F is controlled by the maximal, say, controlled by the maximal function applied to F, Hardy-Littlewood maximal function, which is bounded on L2. So we pick up, and of course, this is dilation invariant measure. This is just Lebesgue measure. So this is just the measure of QR to the 1/2 times the L2 norm of F. And remember, that's the bound that we're looking for. Okay? So that satisfies the right bounds. All right? Okay, and now for the main term. All right, so now I'm going to integrate by parts again. And now I have two R derivatives applied to the localized version of this guy. When I integrate by parts, I introduce a factor here, plus another boundary term B2, again, that you get up at the top, which is, again, is handled more or less like B1. Again, this is an exercise. Okay, and what about this second main term here, which I'll call, I don't know what I'll call it. I'll call it I, for lack of a better term. All right. So then what do we do with I? Well, we distribute these R derivatives. This is going to be, well, there's going to be a term where both R derivatives land here. There's going to be another term where the derivatives, there's one R derivative here and one R derivative here. And finally, there's going to be a last term where both R derivatives land here. Okay, and let's give each of those names. We'll call them I1 plus I2 plus I3. So as in the analogous thing that we did in lemma 5, okay, it's that all the terms are going to be handled in more or less the same manner. So to save time, maybe I'll just explain how to do the first one, and the other ones are left as an exercise of a similar nature. Okay. Okay, so I1 is going to equal, all right, what am I going to do? I'm going to bring this operator dn, this truncated half-order, smoothly truncated half-order derivative, the localized half-order derivative, over onto the PR. I just pick up the adjoint of that, but that's no problem. That just means I'm replacing, with the parabolic fractional integral, I'm replacing the heat operator H by its adjoint. All right, so this becomes dr squared of A tilde R dot times, well, I can even be specific now. It's not just dot xt times dnr star applied to prf at xt, and then I have r dr dx dt, and then I apply Cauchy-Schwarz. Of course, the limits here are the same. I won't keep writing them down to save some time, but they're the same. No, I should be a little more careful. See, the PRF is localized, right? Because F lives in QR, little r is less than or equal to 5r, so we're always here integrating in Q6r. So maybe I should write them down just to be a little bit specific. Okay, so this is integral 0 to 5r Q6r. Okay, because of the constraints on the support of F. All right, so then I use Cauchy-Schwarz. This will be less than or equal to integral 0 to 5r integral Q6r of r times dr squared A tilde of r xt squared dr over r dx dt to the 1/2 times, and at this point, for this guy, I don't care. It can be the entire half space. And then I have dnr star. This is a p, so pr of f of xt. But I should have put an r here, and then it's dr over r dx dt to the 1/2. And call these two terms, let's say, A times B. And then what we notice is that as in the proof of lemma 5, this guy is a nice parabolic Littlewood-Paley operator, a nice QR type operator. The fact that we've truncated the fractional integral is totally harmless. In fact, it makes it even a little nicer. Okay. The cancellation comes from the t derivative that's embedded in here. Okay. So this is r dnr star of PR equals QR is a nice, pretty nice anyway. It's not compactly supported. Well, it's not compactly supported at the scale of little r, but that doesn't matter. Okay. It's a nice enough parabolic Littlewood-Paley operator. Okay, so what we have here is a nice parabolic vertical square function. So B is less than or equal to the L2 norm of F by parabolic Littlewood-Paley theory. All right. And what about this guy? Well, this guy, we just use limit 12. Right, which was the Carlson measure estimates, local square function estimates for the derivatives of A tilde. Okay, and that product is exactly the bound that we wanted. All right, so this is what we wanted. Okay, and the other terms, as I say, terms I2 and 3 are handled similarly. Okay, so modulo lemma 10, this concludes the proof of the main theorem. Modulo lemma 10. All right. So I'm not going to have time to completely prove lemma 10 for you, which, if you recall, were the local square function estimates for the green function, but I can at least explain the basic idea. And after that, it's really not hard. Okay? All right, so remember what lemma 10 entailed. This was the lemma whose proof we had deferred till the end. Okay? It said that if we look at the local square function estimate on omega double star of delta, distance to the boundary, times dt of g squared, plus delta times 2 spatial gradients of g squared, plus delta squared times a spatial gradient times dt of g squared, times 1 over the distance to the boundary, that delta is this delta, dy naught dy ds, that this is less than or equal to r to the d. Okay, that's what remains to be proved. All right. So first reduction is to say that it's enough to look at this term. Okay. Okay. So what you notice is that, remember G, we were looking at G in the adjoint variables. So this is an adjoint solution. So dt of G equals minus Laplacian of G. So immediately this guy gets turned into, can be rolled into this term. And also by local interior estimates for caloric or adjoint caloric functions, you get to throw away a derivative at the expense of getting up 1 over the distance to the boundary. So we can throw this away, drop this power by 1, and we're down to dt. I'm hand waving a little bit because you combine this with a local boundedness estimate, okay, of Moser type, although for the heat equation itself, or adjoint heat equation, it's more elementary and classical. All right. So we can say that delta squared grad dTg in absolute value is less than or equal to delta times an L2 average over a surface, or not a surface ball, over an appropriate Whitney type ball of just dt of g. Okay, where this ball, the radius, the parabolic radius of the ball is like delta, but with dividing by a large enough constant so that the ball is contained in omega triple star. Okay? All right. It's the nature of the relationship between the double star and the triple star. Okay? And then you just use Fubini, and again, you roll this guy back into this term. All right? So at that point, enough to prove with a slightly fattened version of the domain, omega triple star, that delta times 2 spatial gradients of g squared times 1 over distance of y dy naught dy ds is less than or equal to r to the d. All right. So let me observe a couple of things. First of all, I'm going to break up one of these gradients into its constituent pieces. So this is the same as a sum, I equals 1 to n minus 1, integral over omega triple star of, and then I'm going to bring this delta squared out and cancel. This will cancel one of those, and I have grad squared g of y squared times delta of y dy. Not sure what the question is. Where's the index I? Oh, yeah. Oh, thanks. That's the question. Yep, thank you. Yes. Yeah, sorry, you're right. Yeah. So gradient and then di. And then I'm going to write, each of these terms is going to be handled the same way. So I fix an I and set u to be dxi of g. All right. Okay, just a minute or two more. All right. So then here's the basic idea. Without getting into a lot of details, let's recall that, what lemma? I've forgotten my numerology. But we had a lemma, or maybe a corollary 7b. I think it was corollary 7b, which is that G tilde is also, right, that G tilde being the adjoint green function. So G tilde of y is G of y with pole at the at the time backwards corkscrew point. Okay. We also had that this guy is comparable to delta within omega quadruple star. All right. Which means that we get to replace distance to the boundary by this guy, which is a solution, right? A solution of the heat equation. All right. Whereas the U is an adjoint solution. Okay. So we're looking at grad U squared G tilde. Okay. So replace delta by G tilde, which is comparable to it. All right. And this is an adjoint solution. Okay. Since H star of U equals 0, that says that grad U squared is the same as 1/2 Laplacian plus dt applied to U squared. All right. And then modulo some hand waving, because you have to be a little careful, especially with time integrations, because you have a time varying boundary. But what you do is you just integrate by parts. And you move this over to here. Okay, and it kills it. All right? It kills it because this is a, right, when you bring the adjoint heat operator over, it becomes the heat operator, and this is a solution, so it kills it. All right? Then you pick up some boundary stuff, and what you show is that the boundary stuff is okay. It gives you the right estimate. All right? As a practical matter, you don't really do boundary stuff. You make a smooth Whitney decomposition, which lets you deal with time derivatives, but it works. And effectively, it's morally like boundary terms. All right? And that's it. So thank you very much for your attention. Are there any questions?